Ryan Wisnesky, CTO and co-founder of Conexus. Welcome to the Data Exchange podcast.
Thanks for having me.
So Ryan, before we start talking about the kind of the technical areas that we're going to delve into at a very high level and very briefly. So what is ConexUS?
So Conexus provides next generation data integration and migration software and services, knowledge graph construction, ETL, those types of data wrangling tasks.
And does ConexUS specific to certain industries or verticals or more general?
It's more general. What typically defines our applications are those domains that require a high degree of assurance about the meaning of data that's being integrated or migrated.
So then when the rubber meets the road, that means what? Healthcare, finance?
Those are very common areas. Also things like engineering, places where privacy and security are paramount. I'd say you're right.
So a mutual friend connected us together because the underlying, I guess, techniques to your technology comes from math. And specifically an area called category theory, which I must confess, Ryan, I was much more on the applied side, so PDEs, and actually I also did a little bit of stochastic PDEs towards the end. But so algebra, not so much. Although I had to pass at least one exam on algebra, I guess, at the quals level. But I don't think a typical grad student knows that much about category theory, so I would count myself in that category. I do remember. So correct me if I'm wrong. Isn't there a famous book by Saunders Mac-Lane? I can still picture the binding. It's like a Springer Verlag book, right?
Categories for the Working Mathematician, I think, is the one you're talking about. Yeah.
All right. So category theory for mere mortals. So what is category theory?
So truthfully, if you can handle PDEs and such, I think you can handle category theory. It's the way I like to think about it is graph theory, but a little bit more so. So are you familiar with the basic concepts of graph theory?
Yeah.
Okay. So take a directed labeled multigraph. So nodes, edges between the nodes, they're directed edges, and as many of them as you want between the nodes. You can have self loops and that kind of thing. So that's a directed graph. What a category is, or rather a presentation of a category is that graph structure plus a set of equations between paths through that graph. And each of these equations has to start and end at the same place. And so a category is what you get when you equip a graph with like a little system of constraints that relates how the paths through the graph come together.
Wow.
And so
I actually understood it. But in reality, probably category theory can be a lot more abstract than that, right? But what you're demonstrating here is it actually has a lot of practical applications. So any graph where you have some sort of constraint. So with that in mind, so give us some examples of graphs that have some sort of constraint across a few different domains.
Sure. So the common one nowadays, or at least the hype one right now, is knowledge graphs. So typically these have edge symbols that are taken from all across the enterprise. Things like, X bought Y, or Y searched for X, or all the systems in an enterprise have meaning. And so it's knowledge graphs that we see that have a lot of this semantics. Things that say every manager works in the same department that they manage, or so that's one location where we see a lot of the extra structure. Knowledge graphs. Ontologies, that's another related area. You can kind of think of those as knowledge graphs. but more so, those have a lot of this extra structure in them. And then finally, engineering models tend to have this as well. And so these tend to have constraints that actually define behaviors of things like simulations or whatnot. So any of those are just three areas, but there's certainly plenty more. I mean, the reason categories are popular with mathematicians is that they appear everywhere throughout the universe and throughout mathematics. And so we look around and see them everywhere.
And abstract mathematicians also have the superpower where they can see patterns and see where certain things that we take for granted actually have some kind of underlying structure.
Correct. And in fact, they have a very difficult data migration problem of their own. Mathematicians, some may work on PDEs like you were describing, others may work on algebra. How do they take knowledge from one of those domains and transform it into another? They invented category theory for this task. So it's really the study of the structure or the equation preserving graph transformations, you might say. So the mathematicians basically invented category theory to do data integration and migration amongst themselves. And so it's very naturally applied into the real world.
So knowledge graphs are hot now, particularly in the age of machine learning and AI. It turns out that knowledge graphs are quite handy. But you yourself, it sounds like you folks are mostly focused on data integration, right?
Correct. So we see the problem with AI being not so much the fancy models, but the underlying quality of the data. Now, that being said, there is an important application of categories to AI that goes beyond graphs. So you may have heard of knowledge graph embeddings. And so with a category in place of a graph, now you can do learning on something that has constraints. And so using a category instead of a graph to learn on is a powerful way to guide your machine learning with semantics in your knowledge graph.
So take data integration. So can I just do data integration without knowing anything about categories, man? Like 99% of the world?
You can. Good news. There's design patterns in category theory. As you observed, it's mathematicians use it to talk about abstract structure. And so we have a design pattern for doing data integration. You give our system what are called schema matchings and data matchings. So we can help you find these, but they're generated in many ways. Lots of systems do this.
Let me stop you there. So data integration. So there's the EL. So right now, what's hot is EL, right? So and then separate system does the T, right? So extract and load, and then so there's some good startups there, and then some other startups are focused on the transformation. Is that the level of detail that you guys function in terms of data integration?
I mean, we provide services and software that are, front to back. I think that the point I was making there was just that what category theory gives you in this context is like a modular way to separate the merging of data from the finding out what's related to what. And so there's these algebraic constructions that take you from things like these two people are related to here's how I create a database in which you can't distinguish them.
So there's the whole problem of an organization or an enterprise having many systems, in which case they might want to have a unified view of a customer or of an entity. So and then there's the actual mechanics of pulling that off, which would involve not the ELT, but also things like entity resolution, entity extraction. So where does category theory shine
Gotcha.
yeah.
So when you say entity resolution, and I was saying record linkage, those are the same concept. And so what category theory shines is putting those to work, right? It's one thing to find like, oh, these two people, they're probably related because they have similar names, and then making your database such that no way of querying it can distinguish them because you wanted to say that they're the same person. So category theory is very good at putting record links to work, and it gives you an optimally merged database relative to your record links. So,
But so I guess the question is, how does that do? How does category theory do that? Because traditionally people will either use rules, or now they're starting to do some machine learning, right?
right. And so the answer is we do use rules because, as mathematicians, this is all symbolic, but the form of the rules is special in that you can think of a special fragment of logic that's almost been picked out by mathematicians to have nice properties with respect to these types of problems. So the underlying implementation techniques involve automated theorem proving, inferencing engines like you would find in OWL, those types of techniques.
So I'm trying to translate this to something that our listeners would. Um, Typically, people will. So by rules, I mean some sort of regex.
Gotcha.
Yeah. Right. So like this looks like a phone number.
Mm-hmm.
Right. So
right.
James Smith is the same as Jimmy Smith.
Yep.
Right. So.
And so what category theory provides you is a meta logic, if you will, to express rules such as that and other rules, which then get processed by
Ryan, who's doing the expressing of the rules? Is it a domain expert or someone technical, or how does it work?
So it tends to vary. So in many cases, there's a domain expert. We often see these rules generated by AIs. Okay. And so we're agnostic. Wherever the rules come from, we know because of the foundations, we can import them and give you a perfect semantics based on them.
So how does, I guess, so there are other people who are doing interesting things in entity resolution. There's a friend of mine, Jeff Jonas, who has a company, Sensing. I don't know if you're familiar with, so they came out of IBM. So they're pretty good at entity resolution for example, people, addresses, that kind of thing. They can do it in near real time, and they have vast experience in many domains: financial services, hospitality industry, and security. So I guess I'm trying to position your technology in terms of so I can use your technology to do entity resolution.
Here's an example where we would collaborate. So those are very good links at resolved entities. So what our technology does is takes those in and builds a wrapper around an existing database using its inferencing engine so that whenever you query the database, all of that has been resolved, right? It's a way of putting them to work.
I see. So you guys don't necessarily build the entity resolution.
We can help, but that's not what the core of category theory is about. From our point of view, that's like a part of the problem specification.
And so what about in terms of knowledge graphs? Is that an area where Conexus operates as well?
Right. So for us, we think building virtual knowledge graphs is mathematically the same as a data integration problem. It's just one that happens to be, for example, enterprise-wide. And in many cases, you do it virtually rather than actually move bits. But another advantage of the foundation we have is that for us, moving data from A to B and moving queries from B to A are the same. And so sometimes we materialize, sometimes we virtualize, but we see knowledge graph construction as just being another form of data integration.
So there's also a set of open source projects around metadata management that came out of tech companies recently. So there's a project out of Lyft, LinkedIn, Uber, Netflix, Spotify, and a bunch of other companies. So I around 2015, there were some academic researchers in CS who realized that if you had a good metadata management system, you can use that to build many services: data governance, data catalog, data discovery, and so on and so forth. Um, but their starting point is kind of this foundational layer of a metadata management system, which actually it the might be the basis of a knowledge graph as well, for which people can use for data discovery. So where does category? So how does category theory work in terms of what would be a nice starting point for example, for your technology? Like, what would be an ideal uh, situation that you guys would walk into? Like, what already exists?
Sure. So I can tell you a story about the work we've been doing with Uber, and it's related to knowledge graphs. And so they have a federated IT system because of how the company grew up, and they have something like 300,000 schemas and 3 million databases. And so they were looking to standardize enterprise-wide. The issue, though, is that technologies such as RDF OWL and things from 2015 didn't really solve the problem that they needed solved. And so we started working with them to apply category theory to solve this problem. And what we ended up building with them is a schema language for knowledge graphs that is used by them at Uber, so that and with an ontology that they built. It's this technology called Dragon. You can read some blog posts about it. But anyway, combined, what those solve is like a data standardization type of thing, where you get a data fabric where all the data in your enterprise can be viewed in terms of this one formalism about graphs, and then another ontology that is meaningful to your business. So I'd stop there. That may not have been the clearest, but hopefully
Uh,
that's interesting to you.
so take some of the work around RDF. So can you put that in context of what's happening now? Because I haven't kept up with that space.
Sure. So RDF, or maybe we can start with knowledge graphs. So, given the hype around knowledge graphs and graphs being a triple-based format, right? So, nodes go source to target. RDF is getting a lot of attention for being like a lingua franca for triple-based formalisms. And so, the issue is, though, that the idea of triples is kind of what you want in a knowledge graph, not so much all the other stuff in the semantic web, things like how URLs work. And, if you actually read the logical description of RDF and OWL, it's kind of a mess, right?
So
And so,
there's a lot of excess things that you don't actually need for a knowledge graph.
correct. And so what Uber found is that that extra stuff is really getting in the way, and what you want are the triples. But then they found more that you want a little bit more than triples. You want like the data types that are common in systems like Avro and Parquet and all these other more modern things. And so those are all algebraic type systems. And so we were led very naturally to this algebraic notion of property graph that's described very beautifully with the category theory.
So give us a sense of scale. So are these class of tools for small data only, or does it scale to massive data sets?
Good question. So many of the problems encountered in doing category theory are undecidable because you have knowledge representation involved. And so you can think of what we're doing a lot like OWL reasoning or in that class of systems. So the answer to your question is that scalability for us is as good as existing tools. So we have things like chase algorithms and inferencing engines that are comparable and best in class. But that being said, the problems that we're tackling are innately undecidable. And so, I guess you could say that the performance is as good as the theory allows.
But it seems so. So, for example, some of these knowledge graphs can be quite massive, right?
Correct. And so to give you an example, if suppose we're merging two knowledge graphs using this category theoretic technology, then the semantics of the merge is fixed by what category theory says. And the speed at which the merge will happen will essentially be bounded by how fast you can do like recursive, like graph traversals. So it sort of depends on the back end on which you're implementing. So maybe that's another way to.
Is the implementation does the implementation scale out to a cluster, or is it single node?
So the open source tool we have runs on a single node. The commercial versions we have work by code generation. And there, all we really need to on the target to support code generation is relational algebra and recursion thereon. So that's kind of the expressive power that we need to. So things like Spark have that, and so forth.
So if you were to give a talk, Ryan, about category theory to get people excited about its applications, and you had 2 or 3 slides, and each slide had a use case, so what would you put in your talk?
Good question. So of course, I'd have to mention categorical databases because that's near and dear to our heart. But it turns out that category theory has had success in computer science much more broadly. For example, functional programming is a success story of category theory. If you've ever heard of the lambda calculus, the simply typed lambda calculus is something called a Cartesian closed category. So I'd also point out
everything is category theory.
There you go. Yeah.
But so what is a categorical database?
So categorical database, and this is where I'm tempted to get out the slides, but I think we can, since you understood the notion of a graph with equations, so think of that as the schema. So you have a graph, for example, that has nodes like employee and department and manager, and equations that say things like every manager works in the same department as their employees. That's the schema. So essentially a categorical database has as a schema a graph with equations. And then the data is just the regular relational tables where you interpret the edges in the graphs as foreign keys through your tables.
So,
in this way,
implementation would be a traditional relational table. You don't need a graph database.
Correct. It's the schemas that are graphs and it's the data that are tables. However, one of the beautiful parts of category theory is that you can move the data into a graph form and back. So there's some beautiful slides on this, but it's a dual representation. You could also pick a graph representation for the data. But yeah, in practice, we find it's the tabular form.
So are there some well-known applications of categorical databases?
So, we're I guess you could say we're trying to create them. So the work or the discovery that we're commercializing, it's been, presaged a little bit in the literature, but it is fundamentally new. And so, the use cases are essentially traditional data migration and integration tasks, but where it's important that you need to preserve semantics. And so if you think about, tools like Informatica, these schema mapping tools, you can imagine how those work, except now we're mapping these graphs to each other. And the tool says when you mess up your semantics with your schema mappings. So for semantics preserving schema mapping would be the dominant use case.
So is one of the challenges here, Ryan, just basically somewhat of an educational challenge, right? So most companies have people who are familiar with traditional data integration tools or traditional ways of thinking about data that don't involve category theory, right? So in many ways, you have to go into a company and they're either stuck, they can't get something accomplished with existing technology, or
Yes.
or you just go and have some kind of bake off and you just blow away the existing. technology, right?
We have done a few nose-to-nose comparisons with existing ETL tools, but in practice, we tend to find it is more people that have been stuck and that need to do something next generation for which they don't know how to do it now. And then they reach out because, yeah, there's just no existing tools, whereas category theory and our tech can often solve what they're doing, formalize it and solve it relatively easily. So we see more new capabilities than just better, faster, cheaper. But we've
Is there a way for you to describe one of these situations where a company was stuck without revealing any kind of confidential or proprietary information, and
Sure.
describe kind of the high level what uh, what problem they encountered that they felt stuck with existing technology.
Sure. So there is a deployment we did where a avionics manufacturer is testing drones. And as the drones are in flight, they need to test out or swap out testing packages. And these testing packages all operate by executed queries on an SQL database. And so they gave us this problem where they had SQL schemas and they had schema mappings between them, but they didn't know how to transform queries along the schema mappings. And so we gave them a query rewriter that allowed them to essentially reverse SQL queries and then translate them onto a different schema. And so while these drones were in air, our rewriter was essentially creating new test packages on the fly by translating test queries onto new schemas along mappings that were being generated by an AI while the drone was in flight. So query migration, you might call that.
So it's basically two sets of SQL queries.
Two schemas, and then the connections between the schemas were being given by a black box. And then there were like tests being run against those databases. And so what we did was take the test queries and rewrite them along the connections between sources and target. And so they get new queries to run. So basically transporting SQL queries from one schema to another in a way that guarantees they behave the same way as Title used to.
So you also have a paper that you folks wrote called Informal Data Transformation Considered Harmful. So tell us a little bit about this paper.
So yeah, that paper, and of course, we're all very proud of the name, is a crystallization of this premise that we've hinted at today, but haven't really stated, which is that in a data migration and integration context, informalities lead to technical debt. That when you do, hire an army of programmers to transform your data, and then you have to do it again and again, and you're constantly rechecking, like that's a very different world where your data is connected formally through declarative schema mappings that AIs can reason about. And so the premise is that people should really certify their ETL and data transformation processes and make sure that those respect semantics rather than like process their data and then try to fix data quality after the fact and then transform it again and then like check it again for different purpose. That we want to verify the ETL processes rather than the data sets.
And so in terms of practicality, what you described here obviously needs to be done by someone like an analyst or an engineer. So they won't know that much about the math of what you're describing, right? So what kind of what does the UX look like for something like this?
Great question. So the user interface looks a lot like a schema mapping tool. What's fundamentally new about the technology is that the AI can check if you're doing your schema mappings in a way that preserves semantics. So you can imagine something like Informatica, if you will, that stops you when you draw a bad line, because that's going to break the association between managers and departments, for example. And so, yeah, a grammar checker on top or something like that.
So none of the existing tools have some sort of checks for schema mappings?
So there is, of course, syntactic validation, and things like referential integrity in
Yeah.
SQL can be checked. That was sort of the point of these schema mapping tools to begin with, but they cannot check arbitrary logic. And so, that's a tough problem that our AI tackles head on. And it's much different when you're checking arbitrary semantics than just things like referential integrity like existing tools do.
So in other words, if I'm going to migrate some data from this system to a data warehouse, let's say the data warehouse has a star schema. I don't know if you're familiar with this terminology, right?
Yep.
So your tool can help me do that. So that so in other words, I can design the star schema for the data warehouse, and then your tool can make sure that as I'm doing the migration into the data warehouse, I'm actually preserving everything, all the relationships that need to be preserved.
Correct. Let me give you a very concrete example. If your data warehouse is denormalized and you have a bunch of attributes that are just derived, you can write those down as the equations over the schema. And then the AI can check that the queries you write will, in fact, populate those correctly, all at compile time without looking at your data.
So why did you folks just, I guess, I know the answer because there's a lot more budget for data integration than knowledge graphs, right? So, but was there any other reason? So knowledge graphs also seems to be heating up, right? So, but obviously you folks in your company at least chose to go down the data integration path. So is knowledge graph something also that you folks are paying attention to?
So the genesis of this discovery goes back to 2011 in the math department. So knowledge graphs as the concept may not have even existed back then. So, one answer to your question just is that our own backgrounds are in conventional data integration. And so that was a logical place to go. And in fact, we see nowadays a lot of people talk about wanting to have knowledge graphs, but not so many people have them. But given the definition of what they are,
Or not so many people are willing yet to or have budget for them, right?
yes, definitely. A lot of people are saying 1 to 2 years now is the time frame for their implementations, but seems like a natural fit just based on what knowledge graphs are. Add semantics to graphs. That's what a categorical database schema is.
And so, what about Ryan? So obviously now we are also operating in a world with more emphasis on security and privacy. So can category theory help me when I need to remove Ben Lorica from a database based on GDPR? Can it just go and easily purge records? You know what I mean? So is there are there applications in the privacy and security realm as well?
There are. So we like to think of it a little more broadly in terms of policies. But if you think about this, how I was talking about semantics preserving schema mapping, that's a lot like having a semantics preserving query. And so we have use cases where a data architect puts something like a permissions lattice in a data model, and then other people go to query it, but they do so in a way that is against the privacy model. And the AI says, no, that's not a semantics preserving thing that you can do, and it will stop you. So there is a way to use this technology to enforce policy-based access control on a database. Let me give you another example. We worked with chemists that were merging chemical data, and it's imperative that this data not be misinterpreted. And so some of the scientists would create rules that say things like water and sodium can't touch, and those would need to be preserved so that ice and solid sodium can't touch. That's a kind of policy that you can encode and this technology can check. So the answer is yes. It's not a substitute for things like homomorphic encryption or anything like that, but the ability to preserve semantics lets you enforce policies at the query level.
What about this? This might be somewhat of an odd question, but I think it's increasingly coming into play, which is data fusion in the following sense, right? So I have a system over here, and I want to join some of this data to some data over here. But I don't want to do it in a way that violates someone's privacy. You know what I mean? Because if you have an isolated piece of information here, you merge it with something, before you know everything. Right?
Right.
Yeah.
Oh yes, that comes up in a lot of places. We call it being non-conservative, and so when you integrate data in our tool, you'll get warnings that you have like too many consequences of what you're bringing together. Like, oh, euros
And how does
in equals dollars. Like,
how does your system know this?
it's the techniques in the AI. So these are based on algorithms from automated theorem proving. Some are similar to what you'd find in OWL reasoners, but it's all based on that deep computer science of automated theorem.
But does it say? So does that kind of warning? Is it absolute, or does it say something like, well, there's 90% probability that if you do this, you know what I mean?
Yes.
So, yeah.
In this particular case, the check is conservative. It's impossible to give a fully precise check, and so there will be occasions where we issue this warning that the data is in fact consistent, and so that's just what happens when these are all undecidable.
But then the warning, do you guys kind of put the warning in context? So like this is like a triple red alarm. This is a.
I'll give you an example. So we're doing some work with this thing called the FIBO ontology. So this is a financial business ontology written in RDF OWL. And so, as we're working through it and accidentally over integrate our data, the tool will say like, oh, your schema mapping is wrong. It says that as a result of something you did, dollars and yen are the same, and here's why, because of these sequences of things that you did. So it's a nice level of protection against over integration.
So then the other thing that's happening, again related to data fusion, and something that I alluded to earlier. In fact, one of the things that people seem to be headed towards is this notion of a customer data platform, where they have 360-degree view of someone. And part of that is this is that there's just so many systems now, right? So that people touch and use. So I imagine even in your startup, if you go to your IT guy and ask, or gal, and ask them, how many systems do we use? You must probably use over 100 systems, right? From billing to this customer wants to get paid this way and that. So there's so many different systems. So it seems like this whole data integration, data fusion, and just getting your data under control is increasingly gonna be critical, because without that solid data foundation, you might be in the garbage in, garbage out situation, right?
Exactly. And that foundation needs a good meta model, or you won't be able to do what you just said. You might think of things like UML. Why wouldn't you use that here? And it's not.
Or you need some kind of framework that gives you some confidence that it's not duct taped, right? Because basically, as the number of systems are growing, if it's duct taped, then it's going to break, right?
Right. And that's exactly what category theory gives you. Merging two OWL databases in category theory is the same algorithm as merging two relational databases, as merging two graph databases. And so we propose category theory as that meta model.
So let's move a little bit away from category theory for a second. So where do you land in this use a graph database or not use a graph database? Because some of the knowledge base people, actually many of the knowledge base people, don't actually use graph databases for performance reasons.
Right.
So in other words, this graph database, there's more companies and they're doing well, but on the other hand, do I really need my IT people to manage another system and learn another system, right? So if I can get by without using it, it makes a lot of sense, right?
Absolutely. My heart goes out to graph database implementers because it's such a tough problem. From our point of view, we are not a data store, so we're just happy to connect graph database A to relational database B. But I wouldn't want to say relational databases are a replacement for graph databases because they're typically queries you run on graph databases that you wouldn't on a relational one.
That are awkward and right, that are awkward to run. Yeah.
And also graphs are usually sparse. And so it's like relational databases don't tend to have lots of nulls. And so they're kind of two different worlds.
Yeah. So what's next in the area of category theory applications in your mind? So there's data integration, there's knowledge graphs. So what's next?
Well, we've got our hands full just with that, but there is a broader research program for category theory. There's even an institute now for category theory research called the Topos Institute. And the idea there is to apply category theory to other areas of computer science besides data integration. And so people now are working on applying category theory to natural language processing, to speeding up matrix multiplication, to all sorts of things. And so it's a burgeoning field. I'd encourage people to get involved.
So any interesting things of those two things that you mentioned? So are there interesting applications of category theory to natural language?
Absolutely. So, it's getting a little out of my expertise, but some of the axiomatizations of natural language are categorical structures. This notion of composability that you have with category theory appears in natural language. Work on distributed systems now. There's categorical structures being graph-based or being deployed there. I mean, I can't even begin to. David Spivak wrote a book, An Invitation to Applied Category Theory, 7 sketches. It's a great place to start.
So in terms of data integration, so if you were to look ahead 18 months, do you think these techniques will be more common? Because I guess, like we mentioned earlier, there's the educational aspect, but maybe that can be overcome by tools if the tools are a little more accessible.
Correct. So, for us in particular, that's our path forward, is smaller services that are end-to-end offerings that are easy to use. Absolutely.
And by the way, Ryan, in many ways, I don't actually need to know that I'm using category theory, right? So, but on the other hand, someone in your position, you have to kind of mention category theory in order to communicate rigor, right? So that this is what we're doing is robust and rigorous, and unlike some of the previous tools. On the other hand, is there another way of communicating that without actually having to go into the math? So how do you communicate to someone, by the way, so how do you communicate to someone that this approach is better in data integration? So in the data integration field, right? So in machine learning, you go, well, my model is more robust, it transfers better, and the error rate is lower, right? So in data integration, what are the metrics?
So I mean, one metric, like you just said, is the extent to which your machine learning can, learn what you want. And so there we have theorems that say when you learn on categories instead of graphs, you rule out certain things that you didn't want.
No, I mean, but when you go into a company, they don't know any of the theory, right? So how do you convince them that this approach is better? How do they evaluate you, right?
Right. So it's usually on metrics like they know and love, right? So the analysts care about the data quality of their analysis. The data engineers care about not running their queries over and over and over again. And so they tend to respond well to examples that show, hey, here's a query that's wrong because you missed a join condition, 1 out of 100, our prover caught it. Now you don't have to spend a day chasing it down. So, it tends to depend on who we're talking to, but ultimately having semantics preservation enforced just like a grammar checker. Where do you want it? Everywhere.
So basically, so on the data engineering side of things, you can surface in the UI that something to the effect that, hey, your query is hanging because you missed the following where clause.
Correct. And in
Right.
fact, one of the microservices that we have takes SQL code and does a foreign key analysis and checks if you could possibly dangle a foreign key ever. And so that microservice is actually a product we offer now. I have a credit card.
So
yeah.
on the analyst side, you mentioned data quality. So so if you go into a place and how do you demonstrate this to the analysts that you've improved data quality?
Gotcha. So we're fortunate that the category theory gives us a theorem that says when we integrate data, there will always be a unique way to map it to any other integrated data set that is also consistent with the original problem statement. And so we can show them examples of data they've integrated and how we do it. And then we can show our data has fewer rows. It has less nulls. It has more resolved entities, and quantify the information difference. And then it's category theory that makes things optimal.
And but that just surfaces in the tool in the UI, right?
Correct.
You're not showing them theorems, right?
No. Although, it's tempting from time to time.
But then I guess the other thing you can show is, look, you know what? That old report you ran is wrong. Because your tool was able to give you some example of where their previous queries were giving them wrong results, right?
We've heard some stories where results like, oh, the query was wrong. That's not always in an executive's best interest to bring up further up to the attention. So that's a great one, but it often gets a counterintuitive reaction, like, oh God, what did we cover it up, as opposed to, great, now we'll fix it. But you're right, that's a good one.
So let's close, Ryan, by having you tell our listeners, so what are some websites that they can go to learn more about some of these tools and techniques?
Sure thing. So there's, of course, our corporate site at Conexus.com, but the academic and open source heart lies at categoricaldata.net. And so this is a site we set up in collaboration with MIT, and it has all of our academic papers, open source tools, YouTube videos, links to social media, that type of thing.
And so one last question, which is, we're talking about category theory here, but mostly the applications that we described are in computer science. So are the people working in this field in these applications, do they tend to be in the computer science department or in the math department?
Good question. We've seen both. So our co-founder was in math. There's computer scientists at CMU, or category theorists at CMU, who are in the philosophy department. You see it all over. Some category theorists, though, do work on applied math type of questions. And so there's matrix multiplications. How can category theory speed that up? So it's becoming even more applied, like within the last few years or so.
But just to reassure the rest of us, everything is based on theorems, right?
Everything's based on theorems.
And
all the way down. Yep.
With that, thank you, Ryan Wisnesky.
Thank you.